Hey, what's up guys? In this video, we're going to talk about complex numbers. I'm going to start by talking about the imaginary number, and then I'll go into the complex plane and complex numbers. And then I'm going to go into this thing called Euler's formula, okay? It's a very powerful formula, and if you already know what a complex number is and you're just interested in seeing the proof of that and what that's about, you can just skip to that part of the video. And I'll also be going over Euler's identity, which is just an extension of Euler's formula. So let's get started. So I'm going to start by asking the question, what is the square root of -1? And you might immediately be thinking, well, there is no answer. Or maybe you already know that we made up an answer for it. But let's pretend we don't know what the answer is. Well, when you ask what's the square root of something, you're asking what number squared gives you the thing inside the square root, right? So what number, when I square it, will give me -1? Well, there isn't really a number that we know of that can square to -1, right? So I'm drawing a number line here, and on the number line we have positive numbers, right? Obviously, positive numbers squared are just going to give you a positive number, so it won't give you -1. But negative numbers also, when you square them, they're going to give a positive number back. So nothing here can give you -1, nothing here. 0, of course, squared is just 0. So okay, it's none of these numbers. So what does that mean? Well, it means whatever the answer is, it's not a real number. So these numbers here, all the numbers on this number line, are called real numbers, okay? We use this symbol, this special looking R, to symbolize the real numbers, and they include all the numbers from -infinity to positive infinity, okay? All the integers, all the numbers in between, like fractions and irrational numbers like pi and e, okay? So these are all the real numbers. So it's none of these numbers. So what can we do? We can actually make up a new number for it, okay? It's not going to be a real number, so we say it's an imaginary number, okay? And we're going to use the symbol I for imaginary, okay? And so we're going to set I equals the square root of -1. And so this is the imaginary number, okay? So we made up a new number for it. But you might be thinking, okay, how can you just do this? Doesn't that just break math? Well, no, it doesn't break math at all. I mean, I just defined a new number. You might be thinking, well, why can't we do that for other expressions that supposedly don't have an answer? For example, when you divide by 0, okay? When you do 1 divided by 0, this is undefined, the answer. The reason is because if you look at the graph of 1 over x, okay, it looks kind of like this. When you get to 0, from the left side, you go to -infinity, and from the positive side, you approach positive infinity. So right at 0, there's no answer. It's both positive and -infinity. There's no answer that'll satisfy that. So that's why it's called undefined. But what if we just ignore that and we set this to a new number called u for undefined? Well, this does break math. Okay, this does not work because now I can multiply both sides by 0, and all of a sudden I get 1 equals 0. Okay, that's bad. We don't want that. That just causes more problems than we started with. But I is perfectly fine, okay? It equals the square root of -1. If I square both sides, then we see that I squared is -1. If I multiply by 0, it just gives me 0, right? If I add I plus I just get 2i, right? So it works like any other number or variable in math. So there's nothing wrong with it. But why should we do this? I mean, okay, it works, but it's not a real number. So for practical applications like physics, how can imaginary numbers possibly be useful? Well, it turns out they're actually extremely useful. In fact, imaginary numbers show up literally everywhere. Like every particle in the universe, the way we model it, it involves imaginary numbers. And basically the entire reason is because of Euler's formula, this relation here, okay? But we'll get to that. We'll get to why this allows us to work with imaginary numbers, and we can apply it to real life things like in physics. But let's not get ahead of ourselves. Okay, I'll get to that soon. Okay, so with this new number we created, I can now take the square root of any negative number. For example, the square root of -4, well, this is equal to 4 times -1, right? Okay, and if I split this up, this is square root of 4 times square root of -1, which is, of course, 2 times I. Okay, so 2i is another imaginary number. All the imaginary numbers are a multiple of the the imaginary number itself, I. So I want to represent these imaginary numbers now, just like I did before with the real numbers. So I had my my real number line, okay, I'm going to mark it RE for real. And now the imaginary numbers are, of course, not on this line, right? So I'm going to draw a new line for it, okay, a new axis, okay, and I'm going to mark it IM for imaginary. And so this here is the complex plane, okay, and numbers on it are called complex numbers. So all a complex number is, for example, Z is going to be a complex number. All it is a combination of a real number and an imaginary number. So for example, 1 plus 2i. So that's a complex number. It involves an imaginary number, 2i, and a real number, 1. Okay, so the way that this plane works is the coordinates on the real number axis show me the real part. So for example, 1. So I'm going to mark 1 here. And then the imaginary part of the complex number is 2. So the imaginary part is just the number in front of the I. Okay, so then I'm going to go 2 here. And now I can represent Z with a point, okay? And this point, the coordinates of this point show me the real part and the imaginary part, okay? And since this is a point on a plane, I can represent it by a vector that points to that point. Okay, so this vector is Z. So I'm going to put Z here. And just to show you, in general, what Z is, a complex number, it involves a real component. The notation for that is the real part of Z, RE of Z, plus I times an imaginary part, an imaginary component, okay, IM of Z. Okay, so this is a complex number. Okay, so since this is represented as a vector, it of course, just like any other vector, has a magnitude, okay, magnitude of Z, and an angle, theta. So the magnitude would just be, you can just use Pythagorean theorem, right? So it's just the hypotenuse of this right triangle, okay? So the height of this triangle is of course 2, the base is 1, okay? And so the magnitude of Z, in this case, squared, would be 1 squared plus 2 squared, which is 5. Okay, so the magnitude of Z would be square root of 5. But I want to write this out a little differently so that I can show how to get it in general. So I want to write this in terms of the real and imaginary parts. So I want to get it into a form that looks like what I have right here. Okay. So what I'm going to do is I'm going to use the fact that I squared is negative 1. Okay, so just remember that. So what I'll do here is I'll put in an I here, and when this gets squared, that'll turn to negative 1, so I have to put another negative out here. And now if you recognize this, if you did high school math, you should recognize this as a difference of squares, so it can be factored like this, with a product of the conjugates. So conjugate means you take a plus and you turn into a minus. Now this here is a special type of conjugate called a complex conjugate. Okay, a complex conjugate means that any term that has an imaginary number in it, that's the term that you switch the positive and negative. So if you do the complex conjugate of this, you find the term with an I in it, and then you switch the sign out front. So in this case, from plus to minus. So that means that the magnitude of Z is equal to Z times the complex conjugate. So Z star is the complex conjugate. Okay? So that's how we represent this complex conjugate. And so that's how you can find the magnitude of a complex number. Okay, so I just wrote that out explicitly here. So Z star is the complex conjugate of Z, and this is what makes it a complex conjugate. You put a minus sign instead of a plus sign, okay? Okay, so I mentioned before, right, that imaginary numbers, and therefore complex numbers, show up everywhere, and even though they shouldn't exist in real life, they make everything much better. They help us with the math, okay? And before I show you why, when I go to Euler's formula, I want to show you how this works, okay? So I'm going to show you using the complex plane. I want to give you like a visualization of what's happening, okay? Why this works out in the end. Because of course, imaginary numbers, they're not real numbers, right? So when we deal with a problem in real life, okay, like in physics, what we're doing is we start with some input numbers, okay? And then we do some kind of analysis, we use our equations, we solve the problem, and then we get some output numbers, right? The answer. And of course, since this is a real life, these deal with real life things, what we do is, so this is the complex plane. So these are the real numbers, these are the imaginary numbers on this axis. So what we do is we start with input numbers that are on the real number line. But then when we do our mathematical model or our analysis or use our equations, whatever we're doing, we go into the complex plane to do this, okay? We go into the imaginary direction of the complex plane. So long as in the end, when we get our answer, we go back to the real number line. Then all is good. We started with a real number and we ended with a real number. It just turns out that if we can allow this flexibility of using complex numbers, the math becomes easier. And the reason behind that, I think the main reason behind that is Euler's formula. And so how do we get back to the real numbers no matter what? We use the magnitude. That's right. We just say that the answer is the magnitude of the complex number, and then we automatically get a real number, right? Because the magnitude is a real number. It's a length of a vector, okay? Length is always a real number. Okay, so now let me show you Euler's formula and why this makes working with complex numbers so much better than sticking to only real numbers. Okay, so let's go back to this vector picture, okay? And this time, I'm going to write out z in terms of the angle theta, okay? So if we remember our trigonometry, the real part, which is the base of this right triangle, is equal to the magnitude of z times cos of theta, okay? And then the height of the triangle, which is the imaginary part, right? It's the vertical component. This is equal to the magnitude of z times sine theta. Okay, so I can actually write out z like this. I can write out z equals the real part, which is magnitude of z cos theta, plus I times the imaginary part, magnitude of z sine theta. Okay? Okay, so I can write out z like this. Now I'm going to factor out the magnitude of z, and then in the brackets, I'll just have cos theta plus I times sine theta. Okay? So now I want to show you something that I can do with this expression here. Okay, so I'm going to call this x. So I just wrote this explicitly here. Okay, this is x. And now, okay, what I'm going to do is I'm going to take the derivative of x with respect to theta. Okay? So the derivative of cos is negative sine, and the derivative of sine is cos. Okay? And now I'm going to factor the I out. Okay? And for me to do that, just remember that I squared is negative 1. So the I is going to come out of this here. So that's going to be cos theta. And then when I take an I out of this is going to become I sine theta, because when I bring the I back in, right, I squared is negative 1, so this will turn back into negative 1. Okay? Okay, so hopefully you can notice that this is the same as x. Okay, so actually what we have here is I times x. So the derivative of x with respect to theta is I times x. Now I'm going to rearrange this expression to put all the x's on one side, okay? And then I d theta on this side. And now what I'm going to do is I'm going to take the integral of this expression. So the integral of the left-hand side is ln x, and the right-hand side is I theta, and of course is a plus c. Actually, what you can show is that this this constant c is actually equal to 0, and you can show that by just so you would have to use this, and then using this expression you can prove that c is 0. I won't do that here. It's really simple, but so you can show that c is 0. So I'm just not going to include it. I can rewrite this as x equals e to the power of I theta. So then, there you go, that's Euler's formula. What was x? X was cos theta plus I sine theta. So that means that e to the power of I theta equals cos theta plus I sine theta. Okay, and that's Euler's formula right there. So there's another way you can prove this, and that's using the Taylor expansion. So in my last video, I talked about the Taylor expansion, and at the end I said, can you use the Taylor expansion to prove that e to the power of I pi plus 1 equals 0, which is Euler's identity, which you get from this, okay, just by plugging theta equals pi. I'll show that in a second, but I just want to say that if you want to do that with the Taylor expansion, you would just find the Taylor expansion of e to the I theta, cos theta, and you would find the Taylor expansion of sine theta as well, and then you can show that you can put them all together like this. It's pretty simple. Okay, so now let me take a second to talk about why Euler's formula allows us to use complex numbers and it ends up making everything easier to work with. So notice that what it's doing is it's taking a cosine and a sine wave and rewriting it as an exponential function. So one thing I need to mention here is that you can build any function in the world, any function you can possibly imagine. I think it needs to be like a continuous or something and differentiable, but just given that, you can build any function using a sum of different cos and sine waves, okay? And this is called Fourier series, and I hope to talk about it in another video. But all you need to know for now is that any function in the world, okay, whatever shape, okay, that's not a function, but you know, any arbitrary function shape that I have, I can write that as just a sum of different waves, okay? I add these together and maybe it'll add up to that shape. Okay, so what that means is that this really gives me the power to work with any function and convert it into some series of exponential functions. All you need to do is use the imaginary number to get there. And this is very powerful because the exponential function is extremely easy to work with, right? Why? Because the derivative of the exponential function is the exponential function itself. Same with when you take the integral. Okay, so working with the exponential function makes things a lot easier. And so, like I mentioned before, what we do is we work with complex numbers. So we work with waves that we model with complex numbers so that we can write the waves as just exponential functions. Makes things a whole lot easier. And then in the end, we just say, okay, the actual answer for whatever we're talking about is the magnitude of the complex number. Okay, so we always get a real number in the end. Okay, so hopefully that explains the power of Euler's formula. And you'll see this in the future when I do future physics videos, how Euler's formula comes into play and how it makes things a whole lot easier. Instead of using a bunch of trigonometric functions, we just use e to the I theta or e to the I whatever. Okay, so now we get a fun little identity here if we just set theta equal to pi, okay? So let me just show that quickly. So e to the I pi, so cos pi is -1. Sine of pi is 0, okay? So that means that e to the I pi equals -1. And usually what you write this as e to the I pi plus 1 equals 0. Okay, and now this is called Euler's identity. And it's really one of the most beautiful relations ever discovered because it relates like some of the most fundamental numbers in mathematics, you know, pi, 1, 0, the imaginary number I, Euler's number. It relates these things in such like a simple and elegant way, okay? So this is really just like a beautiful thing. So this is Euler's identity, and you get it from Euler's formula, very simply like this. Okay, so now before I end the video, let me just show you how Euler's, when we represent z using Euler's formula, it makes things much nicer already, okay? So z is of course equal to the real part plus the imaginary part, okay? And we already showed that this is can be represented by the angle, right? So we have magnitude of z times cos theta plus I sine theta. Okay, so that gets you the horizontal and vertical part on this complex plane, which will give you the real part and the imaginary part, right? Okay, but this, of course, is e to the I theta. So you can actually write this as z equals the magnitude of z times e to the I theta, right? As per Euler's formula. And now, watch what happens when I try to do the magnitude of z. So the magnitude of z squared equals, you just multiply z by its complex conjugate, so z star z. And of course the complex conjugate, so this will, the magnitude of z's will become magnitude of z squared. And the complex conjugate, you put a negative in front of all the terms with an I in it, right? And now, this is going to be e to the I theta minus I theta, right? Because you just add up the exponents when you multiply these. Okay, and then so this is 0, and e to the power of 0 is of course 1. So then you just get magnitude of z squared. Okay, so see how much nicer that works out. Now instead of having this sum of terms now, you just represent z like this. it's just so much simpler and so much easier to work with, okay? And it all works out in the end, just like we expect, right? All right, guys, so that's all I wanted to talk about in this video. I hope you learned something, and thanks for watching.